Okay, so you're looking at a PV diagram, pressure and volume. And then when you have a constant pressure process, you would have something like this, right? Because the pressure does not change, so it remains always constant on the same line. If you would have a constant volume process, isovolumetric or isochoric process, then you would have something like this, right? In this direction or that direction doesn't matter, because we're staying always in the same volume, right? But then when you have an isothermal process, that is a process in which the temperature does not change, you have something like this. And perhaps the first time you've seen somebody do this, maybe your professor, maybe in a book, you just didn't quite understand, but then eventually you just accepted it and you started doing it whenever you had a constant temperature problem. Why is that? Well, we're going to see that in this video. Guys, welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easier to understand, easier than your class, easier than the way you've been taught before. So let's talk about the isothermal process. What is that? Well, if you call the ideal gas law, it says that PV equals N or mRT, right? Depending on the units of your constant, your R constant. It can be M for mass or N for number of moles. Well, if you have an isotherm, that means that your temperature is not changing, right? So we can picture a little container. We can put, let's close up this container. We can put a fluid inside this container. Let's go ahead and do oxygen, just for the sake of it. Oxygen. Okay, and then we can do a process to this container. Perhaps we're going to increase its pressure. We're going to increase its volume, decrease its volume. I don't know. We're going to do some sort of process here. Okay, and it's going to change into our second stage over here. The process itself does not matter, but we're told that this is an isotherm process, right? So there's no change in temperature. So in other words, the temperature on this state 1 is equal to the temperature on state 2, right? So T1 equals T2. So what does that mean? Well, if there's no mass, know that if there's no mass leaving this system, okay, then not only the temperature is constant, but also the mass on the right side of that equation is constant. So if you go back to PV equals nRT, PV equals nRT, this whole right side of the equation is going to remain constant regardless of what happens to the left-hand side, right? So we can write state 1 and state 2. State 1 is going to be P1, V1 equals the mass, R constant, T1, and then P2, pressure 2 times volume 2, will be the mass. This mass does not change, remember, and then R does not change, it's a constant, and then T2. But T2 and T1 are exactly the same, so that means that this whole right-hand side is the same. So if that's true, then therefore that means that P1, V1 equals P2, V2, right? And if this is true for any isothermal process. So in other words, what we're saying is, if we're generalizing this, we're saying that P, oops, too big. P, any P, we can do Pn, I guess. Vn will be a constant, right? So no matter what state you're in, as long as an isothermal transformation happens, the P times V is a constant. Why does that matter? Well, if we go back to our graph, we'll see that that right-hand side there is going to have exactly this kind of shape here, which is the whole point of this explanation. So to do that, let's go ahead and do, let's change colors. Do pressure and volume. And that, just for the sake of arguments, let's say that the constant is 2. So P times V has to be equal to 2, okay, just for the sake of argument. So how would that play out? Well, if my pressure is 1, then my volume has to be 2. If my pressure is 2, then my volume has to be 1. If my pressure is 3, then my volume has to be 2/3, right? If my pressure is 4, then my volume has to be 1/2 or 2/4, and so forth, right? Cool. So we can write that down into this graph. Let's go ahead and do half, 1, 1/2, 3, 4, it's too close, oops, 5. Same thing here, 1, 2, 3, 4. Okay, so 1, 1/2, probably half, sorry, half, 1, 2, 3, 4, half, 1, 2, 3, 4. So let's draw down what we have so far. When my pressure is 1, I'm going to have my volume being 2. So that's where they meet up. When my pressure is 2, this is going to be 1. So this is where they meet up. When my pressure is 3, 2/3. Okay, so when my pressure is 3 over here, I have 2/3. So I can take this guy here, divide into 3. Oops. Right into 3, it's going to be somewhere around here, 67, right? Okay, so right there. when my pressure is 4, 1/2, so right on the 0.5. Okay, so this is the kind of behavior that I have so far. Right, so we can probably see where this is going. Well, we can do the same thing for the volume, right? We can just keep going with the time for the volume. One thing that you can note by looking at this relationship here is that another way to think of this is, if you want to, you can think of this that, okay, if this is true, then that means that whatever my volume is will be equal to my pressure divided to 2 divided by my pressure. That's another way to think about it, right? Because that is just, I guess, we can do it, obviously that way is going to make more sense, sorry. Whatever my pressure is, it's just going to be 2 divided by my volume. So let's go ahead and do the table again, just this time inputting the volumes and grabbing our pressures. And then let's do the same value. So if my volume is 1, my pressure is going to be 2 over 1. My volume is 2, it's going to be 2 over 2, that's 1. If my volume is 3, then my pressure is going to be 2/3. If my volume is 4, then my pressure is going to be 2/4, same thing as 1/2. So note there's a perfect symmetry between the two, right? Obviously. And then what would happen here? Well, the same thing would happen, right? When my, When my volume is 1, my pressure is 2. So when my volume is 1, the pressure is 2. That's the point that we had before on our graph. When it's 2 is 1, that's already a point we had before. These are the new guys, right? When it's 3, it's going to be 2/3. So when this guy is 3, this guy here is going to be 2/3. So like about the 67 like before. So about here perhaps. And then when it's 4, it's going to be a half. So like before, we're looking at half here. And that has to meet up with 4. Okay, so what's happening here? Well, something like this, right? Which is quite similar to what you generally draw without knowing why. And how does this continue? Well, it continues for infinity, right? Because as we're getting smaller and smaller values of volume here, our pressure is getting higher and higher, right? Check out this equation here. As my volume goes to 0, my pressure goes to infinity, right? Opposite is true. As my pressure goes to 0, my volume goes to infinity. So as my volume is going to 0, so over here, my pressure is going to infinity, right? So what does that mean? Well, it's going like that, and it's going towards infinity without ever reaching infinity. Likewise, same thing here. As my pressure is going to 0, my volume is going to infinity. Okay, and that's a hyperbola. That's where it comes from, right? It comes from the concept that P times V has to be a constant. Now, if you guys recall, the previous problem we did on the Carnot cycle, we had 2 isotherms. We have one isotherm at 510 Kelvin and one at 1 at 500 Kelvin and the other one at 310 Kelvin. Okay, so what would that look like? Well, it would look like 2 different lines. The 500 one would be the greater one, the one on top. The 310 would be the one on the bottom. They would go, there will be a distance between them, and there will always be a distance between them. In spite of them both going towards infinity, they would never touch, right? Likewise on this side here. Okay, and I actually let's jump into another app in which we can plug these equations in. Here we are, and you'll see on this app that I've plugged in the 2 ways that we just talked about. Okay, so I said that x times y equals 510. Note that I'm ignoring mass and r just for the sake of argument. And over here, I'm doing, instead of y times x equals 310, I'm just doing y equals 310 divided by x. Exactly the same thing. Okay, so the smaller one is the green one, the 310 is the green one, the 500 is the blue one. I'm not sure if it's 501, it's supposed to be 500. Not going to change anything, let's just fix it up. Okay, so that's the blue one. And you'll see that obviously there's a distance between the two. And if we zoom out enough, it looks like they are touching, right? So check out, we're zooming, we can go all the way to 7,000 here on the y-axis. It looks like they're touching, but if we zoom in enough, we'll see that actually there's a distance between the two, and there's always going to be space between the two wherever we go, right? And the same thing applies if we go to the x-axis, right? If we go down to the x-axis, it looks like they're touching. We can go down a lot if we want. This is 500 already, but if we zoom in enough, we actually see there's a distance between the two, and they will never touch. Right? That's why isotherms look like that, because of the relationship between PV always being a constant value, and that ends up having a pattern like so. So the next time that we see a PV diagram and we see the drawings of the 2 isotherms, we know that's the reason. But what if we don't have a constant mass process? What if on this process here, we actually have a mass changing? Does that negate the whole thing? Well, not really, right? Because what we can do with this equation here is, if we're savvy enough, is we can instead of consider the volume, we can consider the specific volume. So we can rewrite this as, so we have PV equals mass RT, but this can be rewritten as pressure times specific volume equals RT, right? So then again, this is always constant, and then this multiplication here is always constant. This is already considering the mass, the volume, and the pressure. Okay, so that's when I'm doing the graph, instead of doing a graph with pressure and, and volume, you might see that sometimes we have, instead of volume, we have specific volume. And that's precisely because it's taking into account also the mass that might be changing and when the process is occurring, right? So the same thing occurs. We still have a constant value here because the temperature is not changing, because R is the ideal gas constant, right? So it does not change. And therefore, we would still have this kind of pattern, this kind of drawing happening here with the two lines that tend to go to infinity on both ends, but they never touch. I hope this was helpful. If it was, make sure to subscribe to the channel so you're always up to date with our tips and problem solving techniques. And if you have any questions, just leave them down below. Talk soon.